Electronics, the science that plays a leading role in the progress of modern civilization. Most systems in a modern automobile include microcomputers that control them very precisely to enhance the car's drivability and reliability. These systems are controlled so closely with each other that it is essential for service personnel to fully understand the electrical systems used in the car and to perform troubleshooting jobs accordingly. This video is designed to help you understand the body electrical system and the principles of troubleshooting by using some of the electrical systems found in the LS400 as examples. First, we will study the major wiring system and how to read electrical wiring diagrams. Then, we'll learn about the SRS airbag system, the memory system, the wireless door lock remote control system, the theft deterrent system, and the combination meter in that order. For each system, we'll first learn how the particular system operates, the key points of the system, and then the method of troubleshooting that system. Some troubleshooting repair methods will also be explained. We will start with these four major wiring systems. This is the main wiring harness in the engine compartment. It is connected to the fusible link box, junction block number 2, headlights, water temperature switch, engine hood courtesy switch, horns, etc. This is the cowl wiring harness. It is connected to the front airbag sensors, theft horn, the mirror ECU, theft deterrent and door lock control ECU, tilt and telescopic ECU, center airbag sensor assembly, junction block number 1, junction block number 4, ignition switch, etc. This is the instrument panel wiring harness. It is connected to the combination meter, rheostat, mirror ECU, luggage compartment door opener, remote control mirror switch, wireless door lock main switch, air conditioner control assembly, radio and tape player, junction block number 3, etc. And this is the floor wiring harness. It is connected to the O2 sensors, fuel pump, fuel sender, fuel lid opener solenoid, wireless door lock ECU, luggage compartment door lock solenoid, CD automatic changer, door courtesy switches, etc. Next, we'll see how to read the electrical wiring diagrams for the LS400. Suppose you wish to inspect the SRS airbag system. First, look at the items under the heading System Circuits. And look for the item SRS airbag. On the page indicated, you'll find special precautions about checking the airbag system, as well as the circuit diagram for that system. On the diagram, you will find numbers and letters indicated. For example, 19IH3. The box itself indicates a connector joining wire harness to wire harness. The letter I indicates the connector is located near the instrument panel. H3 is a code that identifies the connector. The number 19 at the left side of the box is the pin number of that connector. Looking at the page following the wiring diagram, you'll find a reference to the page that shows the location of the connector, plus an explanation. Then, by turning to the page indicated, you can easily locate the position of connector IH3 on the body. On the following page, you will find the illustration of the connector, together with the pin numbers of the male and female connectors. Pin number 19 is located here and here. As you can see, pin 19IH3 is located here. Reading electrical wiring diagrams is easy when you refer to the vehicle carefully. Used in combination with the seatbelt, the airbag system is designed to protect the driver in case of a frontal collision. This system is controlled by the center airbag sensor assembly. This is the center airbag sensor assembly. The spiral cable and the squib are located on the actuator side of the system. The system includes the front airbag sensors and also the safing sensors and center airbag sensor, which are located inside the center airbag sensor assembly. The system also includes a diagnostic circuit and memory circuit that are used to detect a system malfunction. Connectors between these components shown here are designed especially to ensure utmost reliability of the system. A special mechanism called the terminal twin lock mechanism is used for all these connectors. The key element in the terminal twin lock mechanism is a wedge-like spacer that ensures terminal connection. The connectors shown here include an airbag activation prevention mechanism. When any connector is disconnected, the short spring plate in the airbag activation prevention mechanism closes the circuit on the squib side to prevent electricity from flowing to the squib. This is the short spring plate. These connectors have an electrical connection check mechanism. When any of these connectors is connected correctly, the connection detection pin makes the contact. This permits a very small amount of electricity to flow to the center airbag sensor assembly through resistor R to check the connector mechanism for its connection condition or open circuit. This is the connection detection pin. These connectors have a connector twin lock mechanism. Connector connectors with the connector twin lock mechanism are locked in 2 steps to ensure that they are connected correctly at all times. When you are inspecting or troubleshooting the airbag system, you must remember which type of mechanism is used in each connector. Now, let's assume that the airbag warning light is on and stays on when it should be off. Let's see how troubleshooting is done in this case. If the system is functioning properly, the light should go off 6 seconds after the ignition switch is set to the ACC or on position. If the light does not go off at all, it is likely that the center airbag sensor assembly is detecting a malfunction. So, to check the diagnostic codes, connect terminals TC and E1 of the TDCL. Code 14 is displayed. When a diagnostic code is displayed, you must check if it corresponds to the particular trouble you are checking the system for. To do so, remove the probe wire from terminals TC and E1 of the TDCL and cancel the diagnostic code once. You can cancel it by removing the ECU B fuse from the junction block number 1 for 10 seconds or longer with the ignition switch turned to the off position. Then turn the ignition switch on and off repeatedly 5 times with an interval of 20 seconds between each time. Next, put the probe wire again into terminals TC and E1 to reconfirm the diagnostic code. Code 14 is displayed again. This code indeed represents an electrical problem, the airbag warning light that does not go off. Code 14 means that the squib circuit is open. Before you begin inspecting the squib circuit, you must first disconnect the negative terminal of the battery and wait for 20 seconds or longer until the backup power source is discharged. You can now begin checking the squib circuit for an open circuit, but remember, never measure the resistance of the squib under any circumstances. This is because if the airbag activation prevention mechanism is not functioning properly for any reason, electricity might reach the squib and trigger it when you measure its resistance. To check the squib circuit, first separate the connector like this, and then measure the resistance at the spiral cable side. Incidentally, connector A41 is not shown in the electrical wiring diagram because it only connects one part to another part. Now measure the resistance across the first and second pins of connector A41. If the system is functioning normally, the resistance reading should be 1 ohm or less because of the airbag activation prevention mechanism. But the meter indicates infinity. This is the result of an open circuit between these connectors. The next step is to narrow down the possible cause of trouble. To do so, let's separate this connector and check the resistance again at connector A41 as before. The reading is less than 1 ohm. This means that the spiral cable is all right. Then the cause of the trouble is most likely an open circuit in this connector. You can check this by measuring the resistance across the first and second pins of connector A29. The meter reads infinity. This means there is an open circuit in this connector, just as you suspected. This trouble can be corrected by repairing the harness between the center airbag sensor assembly and the spiral cable. Let's quickly look at how to repair the assembly. First, put the two open ends of the wire harness through a sleeve, like this. Then, making certain that the two ends are connected correctly, fasten the sleeve by using a crimping tool. To secure and protect the joined connection, ordinary electrical tape and silicone tape are used. First, thoroughly wind the silicone tape over the connection. Then, wind the taped connection with ordinary electrical tape. If the connector is damaged, as seen on the left, replace it with the new one as seen on the right. When this is done, check the diagnostic code again. Code 41 is displayed. This code indicates an old trouble. When a new trouble is corrected and the power is turned off, the trouble code disappears and code 41 is stored in memory. This code is stored in a non-volatile random access memory and remains in the memory even after the battery is disconnected. To cancel code 41, set the ignition switch to the on position and connect service wires to terminals TC and AB of the TDCL. Then alternately ground these two terminals to the vehicle's body, starting with terminal TC. Ground them twice each, and finally ground terminal TC to the body a third time. Code 41 is now canceled, and the airbag warning light will start flashing after several seconds. Let's check the diagnostic code once again. If the airbag warning light indicates that the system is functioning normally, troubleshooting has been completed successfully. Here's an important point to remember during airbag inspection. If you should need to disconnect the power cable from the negative terminal of the battery for any reason, you must check the memory settings of the audio system in the car and record them, because all the memory will be canceled as soon as you disconnect the cable. The memory system is used to memorize positions of the tilt and telescopic steering, outside rear view mirrors, the power seat, and the seatbelt anchorage, and to perform a return operation when requested. This system is controlled by the tilt and telescopic steering ECU, mirror ECU, and power seat ECU. This is the tilt and telescopic steering ECU. It also controls the seatbelt anchorage position. This is the mirror ECU. And this is the power seat ECU. These three ECUs have manual switches. By using these switches, you can operate them independently from the memory system. By operating the memory and return switch of the memory system, the driver can control the tilt and telescopic steering ECU, the outside rear view mirror ECU, and the power seat ECU. This is achieved through a memory or return signal and a reply signal. You can troubleshoot the memory system quickly and accurately if you fully understand the relationships between these three ECUs and related electrical wiring diagrams. We will now perform troubleshooting of some sample problems in order to study troubleshooting techniques. When you press the memory return switch, the outside rear view mirrors and the power seat are adjusted to the programmed positions, but the tilt and telescopic steering and the seatbelt anchorage do not return. In this situation, it is safe to conclude that signals to the mirror ECU and the power seat ECU are functioning normally. You must then determine if the steering shaft and the seatbelt anchorage positions fail to return due to a malfunction of the memory system. You will know the answer when you operate them by using the manual switches. The tilt and telescopic steering does not move at all. The seatbelt anchorage position does not move either. It is most likely, then, that the problem is in the tilt and telescopic steering system and not in the memory system. None of the three motors, the tilt motor, the telescopic motor, or the seatbelt anchor motor, are working at all. When you examine their power sources, you will find that all three motors are connected to the positive terminal of the battery via 4T14. The next step is to measure the voltage across plus B, 4T14, and ground, 7T14, to check if the positive battery signal is reaching the computer. The reading is 0 volts. It appears that the positive battery signal is not reaching the computer. Next, let's check the voltage across plus B, 4T14, and body ground. The reading is 0 again, and you now know for certain that plus B is not reaching the computer. Let's check the 30 amp circuit breaker in junction block number 1 for continuity. The meter reads infinity. This indicates a lack of continuity, and this is why plus B was not reaching the computer. So let's reset the 30 amp circuit breaker. And check if the system functions normally now. If the breaker opens again, recheck the system to find why it opened and correct it accordingly. In this case also, as in problem number 1, the tilt and telescopic steering and the seatbelt anchor positions do not adjust when you press the return switch. When you operate them using the manual switches, the tilt moves a little and stops before it reaches the desired position. But the telescopic adjustment functions normally. The seatbelt anchorage position is adjusted correctly also. We learned a while ago that the tilt, telescopic, and seatbelt anchor motors are powered by the same power source. Since the telescopic motor and the seatbelt anchor motor operate normally, you can assume that the power source itself and the ground are all right. This leaves a strong possibility of a malfunction in the tilt motor or tilt sensor circuit. But since the tilt motor does operate slightly when it is controlled by the manual switch, the fault is probably in the sensor circuit. The next step is to check the computer output and input in the sensor circuit. The voltage at VC should be 5 volts. Let's check the voltage across VC17T13 and E15T13. The meter reads 5 volts as expected. So the circuit is normal. Next, let's measure the input side voltage across TIS7T13 and E15T13. Normally, the voltage should be between 0.8 and 4.2 volts, but the meter reads 4.5 volts. The voltage being higher than 4.2 volts suggests an open in the circuit somewhere between the sensor and terminal E1. You can narrow the problem down further by turning the auto switch on and testing the voltage between output terminal ASW4T13 and input terminal E15T13. When you turn the auto switch on, the meter reading is 10 volts. When you turn it off, the reading drops to 0. It means this circuit is working properly. So if there is an open somewhere, it's probably in here. You can prove it by moving the tilt sensor by hand and see how the voltage changes between TIS and E1. Let's move the lever. The voltage changes suddenly from 4.5 to 0 volts and from 0 to 4.5 volts. If the system is functioning normally, the voltage should change gradually between 0.8 and 4.2 volts. Therefore, the open is inside the tilt sensor. This means the tilt sensor must be replaced with a new one. After replacement, you must check the system again. If it functions normally, the repair is completed. In this final example of problems with the memory system, the power seat position does not return when you press the return switch, although all the other memory systems operate correctly. By operating the power seat manually, you can tell if the problem is caused by a fault in the signal circuit or the power seat itself. The power seat works properly manually. So the problem seems to be caused by a malfunction in the signal circuit. With the ignition switch on, brake lights off, and the neutral switch in the P range, the outside rear view mirror positions are adjusted automatically by the memory system. Therefore, circuits A and B are fine. This leaves the possibility of an open circuit or short circuit in circuit C or D. Let's check the continuity between SO9T13 and SI8P13. The meter reads 0 ohms. This portion is all right. Let's check for continuity between SO17P13 and SI1T13. The meter reads infinity. This means that there is no continuity. There is an open in circuit D, and the power seat does not return because the reply signal cannot return to the computer. If all the circuits are in normal condition, then the malfunction is in one of the ECUs. Replace them with new ones one by one to check them. At this point, let's look at normal return signals and reply signals on an oscilloscope. We will see what's happening at 2 points, SO9T13 and SI1T13. As you can see here, during power seat return operation, return signals and reply signals are constantly sent back and forth. Now let's summarize the key points about inspection of the memory system. First, by operating each system using the manual switches, you can determine if the problem is caused by a malfunction of the memory system or by a malfunction of an individual system. Then you can narrow down the cause of the problem by checking if the input and output of individual ECUs are normal. The wireless door lock system enables the driver to lock and unlock the door from a distance using radio waves. The wireless door lock system is controlled by the wireless door lock ECU and the theft deterrent and door lock control ECU. This is the wireless door lock ECU, and it is located at the left side of the trunk. This is the theft deterrent and door lock control ECU, and it is located at the back of junction block number 1. Door lock control is normally done by the theft deterrent and door lock control ECU. Therefore, the wireless door lock control system is regarded as optional. As such, when you are troubleshooting a problem involving door lock control, you must first determine if the problem is caused by a malfunction of the door lock control system or by another cause. And even if the door lock control system is functioning properly, you cannot immediately conclude that the problem is caused by a malfunction of the wireless door lock system. It may be the result of radio interference. The wireless door lock system must be considered as two parts: the radio wave system, including the transmitter and other components, and all other components and circuits. Now, let's look at some actual troubleshooting. In this example, the wireless door lock system does not function at all. If you encounter this type of problem, you should first check if the door can be locked and unlocked using the key. It's working normally. This means the door lock control system is functioning properly. So the problem must be caused by radio interference or a malfunction of the wireless door lock system. Before you go any further, you must perform some initial checking. There are two types of initial checks. Type 1 is used when the wireless door lock system fails to function only in particular geographical areas. Type 2 applies when the system does not function at all, regardless of the car's geographical location. We will explain here how the Type 2 initial check is done. First, open the driver's door only. Then, using the door lock control switch, lock and unlock the driver's door 10 times repeatedly within 30 seconds. Then, immediately after this, press the transmitter switch and keep it down for 10 seconds. While you are holding down the transmitter switch, count how many times all doors lock and unlock during the 10-second period. If the doors do not lock or unlock at all, it means a malfunction on the vehicle side. Malfunction on the vehicle side means that the problem is not caused by radio interference or by a malfunction of the radio wave circuit in the wireless door lock system. We will now begin inspection of the input and output of the ECU, starting with the power source to the ECU. First, we measure the voltage between plus B, 1W9, and the body ground. The meter reads 12 volts, which means the power source is normal. Let's check the continuity of the ground circuit next. We measure the resistance between E7W9 and the body ground. The reading is 0 ohms, which is normal. So far, we have discovered that the power source and ground are in good condition. Now, the failure of all the doors to lock and unlock may be caused by a malfunction of the circuit that forms the ground on the wireless door lock ECU side, so that the doors are locked and unlocked by the theft deterrent ECU. With the ignition switch set to the on position, let's check the lock control first. The lock control is functioning properly if the voltage at SWL5W9 is 12 volts. The meter reads 0 volts. The lock control is not functioning properly. We check the unlock control next and measure the voltage at SWUL4W9. The meter reads 0 volts. The unlock control is not working properly either. It is likely that there is an open in both circuits, or one of the connectors is faulty. Since both circuits share connector BQ2, which is located in the left-hand cowling, it's very likely that the problem is caused by a defect in this connector. Let's inspect it. See, a pin is disconnected. This is why the necessary grounding was not formed and the door lock and unlock control did not function properly. Push the pin in and put the connector back. The system works normally now. We checked the voltage at SWL and SWUL with the ignition on because there is always a constant flow of current for a consistent reading. If the ignition is off, the reading will be inconsistent. Let's summarize the key points in the wireless door lock system inspection. You must determine if the problem is caused by a malfunction in the door lock control system, or by radio interference, or by a malfunction in the wireless door lock system. This is the first step of the inspection. The theft deterrent system is designed to discourage theft by sounding a horn and cutting the starter circuit. When all doors are closed and locked, either by the door key or the wireless door lock system, the indicator light goes on. After 30 seconds, the light begins flashing, indicating that the theft deterrent system is set. If someone opens a door without using the key, the horn sounds automatically, and the starter circuit is cut at the same time. This system is controlled by the theft deterrent and door lock control ECU. This is the theft deterrent and door lock control ECU. The theft deterrent ECU has two modes, the door lock control mode and the theft deterrent mode. When you are troubleshooting this system, you must determine whether the problem is a result of a malfunction in the door lock control mode or in the theft deterrent mode. Let's see how troubleshooting is done. In this example, all the doors are closed and locked by a key, but the indicator light does not go on and the system cannot be set. This suggests that the ECU has not switched from the door lock control mode to the theft deterrent mode. Therefore, you suspect a malfunction in the sensor circuit that detects the door operation. It is possible that one of these switches does not go off when the doors are closed and stays on due to a short circuit. You can tell which one is causing the problem by measuring the voltage at each of these switches with all the doors closed and the ignition switch set to the on position. Let's begin with terminal BKUL 4T10 in the luggage compartment door key operated switch circuit. The meter reading is equal to the battery voltage. This means this circuit is functioning normally. Let's check the voltage at terminal BCTY 9T10 of the luggage compartment door courtesy light switch circuit. Again, the meter reading is equal to the battery voltage. This circuit is also normal. We will check CTY 7T10 of the door courtesy light switch circuit next. This circuit seems to be all right also. How about terminal RRL 11T10 of the position switch circuit? Again, the battery voltage is normal. How about terminal HOOD 8T10 in the engine hood courtesy light switch circuit? Here, the meter indicates 0. It seems that the engine hood courtesy light switch is on at all times. Let's remove the switch and check for electrical continuity between terminals 1 and 3. There is continuity between these terminals even when all doors are locked. This is why the theft deterrent system could not be set. In the second problem, the starter motor does not operate at all. In this case, you should not jump to the conclusion that the cause of the problem is a malfunction of the starter circuit. This is because, in the case of the LS400, the engine starting system is closely related to the theft deterrent system. As this circuit diagram shows, the starter relay is grounded to the ECU so that the ground circuit becomes open when the theft deterrent system is activated. In other words, you must determine first if the problem is in the engine starting system or in the theft deterrent system. This is done by checking the voltage between ST-T11 and the body ground. If the meter indicates 12 volts, the engine starting system is normal, and you should check the theft deterrent ECU. If the reading is 1 volt or lower, you should check the engine starting system. Let's summarize the key points in the theft deterrent system inspection. First, you must determine which one of the 2 ECU modes contains the problem. You must remember that the theft deterrent system is very closely related to the engine starting system. In addition, you must fully understand its relationship with the wireless door lock system, as we explained a while ago. Otherwise, you will be taking unnecessary steps during troubleshooting. For the combination meter, the dial panel uses a cold cathode tube and the needle uses a miniature cold cathode tube. The warning and indicator lights are of the image reflected type. Let's look at an example of troubleshooting and key points in the combination meter inspection. We will start with troubleshooting. With this problem, when the ignition switch is set to the start position, all meters come on and remain on. When everything is working properly, the meter lighting is turned off while the starter is cranking the engine so that the engine starts more easily. Let's examine this mechanism in more detail. Basically, the meter lighting receives electricity from IG1 1C12. While the engine is cranking, the battery voltage is sent to ST2C12 so that the lights go off momentarily. Let's see now how this mechanism actually works. First, we apply 12 volts to IG1 1C12. This turns the lights on. Now let's apply 12 volts to IG1 2C12. The lights go off. They come on again when the voltage is not applied. Now let's return to troubleshooting. In this case, it is possible that 12 volts is not applied to ST2C12 while the starter is cranking the engine. Let's check the voltage at ST2C12. To do this, you must first remove the combination meter and separate connector C from the meter. Let's turn the starter now. The meter reads 0. This is not the correct voltage. Let's look at the circuit diagram and trace the circuit back from terminal ST. You can see that ST shares the starter circuit up to I12. The starter turns normally, so we know that the circuit is fine up to I12. This means that the circuit is open somewhere between I12 and ST2C12. Let's measure the voltage at B16 IH1. The meter reads 10 volts. Now, since the correct voltage is applied up to B16 IH1, you can conclude that the open is somewhere between B16 IH1 and ST2C12. Finally, let's review some of the key points in the combination meter inspection. First, you must remember that a high voltage is applied to the combination meter when it is turned on. As you can see, the voltage is as high as 940 volts. Therefore, when you remove the meters from the automobile for inspection purposes, you must be especially careful. In this video presentation, we have explained the key points to understanding the body electrical system and introduced some principles of troubleshooting. For more detailed information, we ask you to refer to the new car features, repair manuals, electrical wiring diagrams, high-tech instruction manuals, and other booklets to increase your knowledge. We also recommend that you make full use of the newly developed checkers so that with a correct understanding of the body electrical system, you will be able to perform speedy and accurate troubleshooting.